Pluto is a distant and clandestine, more modest planet that was once a part of our nearby planetary system. However, recent disturbing statements by leading astrophysicists Neil deGrasse Tyson and Maio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this chilly world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing an intriguing cosmic ity, or is there something else to this approaching celestial accident? Join us as we explore the potential results of a Pluton Neptune impact. Pluto, a former planet that was demoted to a dwarf planet, somewhat due to its unusual orbit, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Makaku are both raising the alarm about a possible dangerous collision between these two planets, which could pose a massive threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, wandering extensively from the almost round orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, determined at 17 degrees to the ecliptic plane. The way Pluto follows its path is much more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, challenging what we might expect from their positions in the solar system. This leads to the natural question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unusual path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does in fact cross Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves determining how three objects like Pluto, Neptune, and the Sun move and interact with each other through gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms ASU libration, degree libration, and the VZK oscillation are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is ASU libration with respect to Pluto and Neptune. This term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 9 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Degree libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet it is positioned far above their orbital plane, providing an additional layer of protection from possible collisions. Another important aspect of the situation is the VZK oscillation, named after three scientists, Zelkai and Kaku, who studied how objects move in space. It involves how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull affects how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming erratic, this oscillation ensures it moves smoothly over long periods. The VZK oscillation shows that although things in space seem chaotic and unpredictable, certain patterns and forces keep everything in order. All these factors help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or stray off course. This three-body problem is crucial to understanding how these orbits change because of the way space objects interact with each other. Studying this helps us learn more about Pluto and our solar system, as well as distant planets and their stars. Mathematical simulation in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually tumultuous, with minor deviations in initial conditions leading to significant changes over thousands of years. However, these remarkable properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, keeping the disruption under control. Later computational models have helped us understand how the giant planets like Neptune, Jupiter, and Saturn impact Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only player in this. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, as does Saturn. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a long time, even millions ions of years. So it's as if Neptune, Jupiter, and Saturn are all working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are essential for maintaining order and stability in space. Without these factors, the solar system, as we know it, would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, particularly with discussions about it potentially crashing into Neptune in the future. Understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of the strangeness. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated for Pluto. This means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using computational models has been tremendously helpful for researchers in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, astronomers can see how even tiny changes can make a huge difference in where Pluto ends up in the late 1980s. These simulations revealed something intriguing about Pluto's orbit. Even though it has mechanisms like ASU, libration, and scope vibration to keep it stable, its orbit can still be unpredictable and chaotic if you start with just a small difference in where Pluto is or how fast it's moving. Its orbit could end up looking completely different after a number of years. However, even with this chaos, Pluto's orbit remains stable over incredibly long stretches of time, like billions of years. This means that Pluto's journey around the Sun has a sort of order to it, even though it seems turbulent at first. Predicting celestial events, especially when they involve Earth orbits like Pluto, is a massive challenge. The inherent volatility of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide valuable tools to understand and predict the future paths of celestial bodies, they also highlight the limits of our predictive abilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to drastically different outcomes, making precise predictions an overwhelming task. Moreover, the chaotic nature of planetary orbits like Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case serves as a humbling reminder of how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and direction of other bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event from occurring? Neil deGrasse Tyson, a prominent astrophysicist and a major figure in promoting cosmology, offers an intriguing perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the unexplored realms of space. Tyson's stance on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a downgrade but as an important adjustment, in line with our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of constant learning and adaptation. He views the complexities of orbits like Pluto as a sign of how much there is still to discover in space. The interest in these unknowns is what keeps the study of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's possible collision with Neptune paint a much more uncertain future. He emphasizes that the orbits of Pluto and Neptune will continue to evolve, driven by forces that are sometimes unpredictable. Interestingly, Tyson also mentions that these uncertainties could potentially lead to Pluto getting closer to Neptune's orbit over the next few million years. Despite this, he remains cautiously optimistic about the possibility of such a collision. Tyson's analysis suggests that while the odds of such an event occurring are low in the short term, the unpredictable nature of planetary orbits means we cannot entirely rule out the possibility of such a collision in the distant future. In addition to Tyson, Makaku, a renowned theoretical physicist, also weighs in on the implications of Pluto's potential collision with Neptune. Kaku's analysis combines cutting-edge physics with a deep understanding of cosmic evolution. He believes that such a collision, if it were to occur, could have profound implications not just for Pluto and Neptune but for our understanding of the cosmos as a whole. According to Kaku, a Pluto-Neptune collision might trigger a cascade of other events, perhaps even changing the nature of the solar system as we know it. However, Kaku also acknowledges that the chance of such a dramatic event happening in the near future is highly unlikely. He points out that while the orbits of Pluto and Neptune are in close proximity, the vastness of space and the intricacies of their orbital dynamics make a collision unlikely in the immediate future. Nevertheless, the possibility remains an intriguing topic for further study and speculation in the scientific community. In conclusion, the possibility of Pluto colliding with Neptune remains a topic of active debate among astrophysicists. While the mechanisms of their orbits prevent a collision from happening in the immediate future, the complexities of celestial mechanics mean that we cannot rule out the possibility of such an event occurring in the distant future. The ever-changing nature of planetary orbits reminds us of the dynamic and unpredictable nature of our universe. Whether such an event occurs or not, it serves as a fascinating example of how little we truly know about the future of the solar system.